Sure, sure. All right. Everyone, thanks for joining. A quick logistics, which you guys more or less know. We have a repeated attendees. So the emails that you can reach and contribute towards this good cause, and the fourth link is for you to register in the Eventbrite. We appreciate you registering. In case you're a little bit lazy, you can copy this link and keep it and join bi-weekly. I think this is our 9th session, 3 more sessions to go, right? Or 10th session.
It's a 10.
10, 2 more sessions to go. That's really good. You have no clue how much we have learned, right? I kept on adding slides and kept on teaching you guys or sharing my knowledge with you guys. The number of slides has come to almost like 83, and still 3 more sessions, and I still have lots to cover. But whatever we can cover in next 3 sessions, I will try to at least touch upon all the topics that we decided to learn, right? If not in more detailed, but some topics I'll try to cover in detail, and rest, at least I'll try to give high-level stuff. So more or less, we covered 3 topics, and we are in the 4th topic. And in the 4th topic, the most important thing is this virtualizations and thing, right? The difference between SDN and all those kind of things. That's the most important thing that I wanted to cover. And then I'll probably give an intro to what are all the different technologies and why it is used from the connectivity point of view. And I'll try to see in the last session if I can give you guys some input around spectrum, because if you don't know this, you're not basically complete, right? Whatever that I kind of share with you is a very basic, but at least it will allow you to expand your knowledge. And when you're talking to your customers, it will help you to kind of at least understand what they are saying, right? Otherwise, most of the time we talk something that perceived differently, right? So that's the thought process. All right, so let's see where we were. Okay. All right, so let's do a quick recap, because I wanted to really close this session today. So cloud, we learned it. It is introduced by enterprise mostly. Different types of cloud were introduced. Mostly the cloud were used for deploying the applications, right? Web applications and whatnot, right? Cloud applications and so on. So you had the server side application, and then you had a client side application. So the client communicates to the server, and then it's called client server applications. And the server applications mostly sit in the cloud, and the client applications mostly sit in your devices, right? Whether it's a mobile phone, laptop, or whatnot. Okay. And the most critical thing here is that all the concepts, right? Virtualization, meaning not using a dedicated hardware. You can have multiple people, multiple organizations in the cloud. When you require, you can increase the spend, and when you don't require, reduce the spend, which is elasticity. And you're able to automate it through DevOps, Python, many other scripts. It allowed small companies to become, startups. If you think about it, the startup ecosystem started after cloud, right? Because when you wanted to start a company in the past, it required a lot of investment to start the company. But then when cloud came, you have monthly $50. You're able to pay that $50 to the cloud. You put your own website, you start your business, right? It became innovation, right? And it's kind of distributed. So you can address, like, for example, you can run some of your server applications in Singapore to address the local need of the Singapore latency requirements and so on, right? So these are all some of the key things, key concepts that evolved. And that's the concept. It's not about the cloud, right? The concepts and the benefit is where people started thinking about how do I further disaggregate the network and things like that, okay? So when you talk about that, we started first from the transport side, right? So the innovation happened on the transport side. It's basically business initiators were enterprise, and they wanted to really get rid of using expensive transport equipments, right? And that's when this SDN came into the picture. So it separated the control plane and user plane on the transport layer, right? So all the protocols that you used to do, right, BGP and so on, that all went off, and people started using OpenFlow, XMPP protocol from a central location to kind of manage all the boxes and tell the boxes if a IP packet comes from A, ship it to B, right? So that's how it was introduced, SDN, and SDN is mostly on the transport, right? This is my hand-drawn diagram just to kind of explain, right? You have an access, and it's mostly on the transport side is where the SDN is used. Then we introduced in our last meeting, last session, the NFV. So NFV is on the application side. Now, when I say application side, it's layer 4 to 7 in the telecom side, right? Not the actual web app, the server application and client application that I talked about in cloud. So here, what they wanted to do is they want to get rid of, in SDN, they want to get rid of expensive transport equipments, and they want to become automation and innovation happening there. In NFV, what they wanted to do is they want to get rid of expensive layer 4 to 7 equipments like session border controllers, MMEs, P gateways. They want to get rid of all those things, even brass, right? So all those firewalls. So they want to get rid of all those equipments that support 4 to 7 functionalities. And they wanted to softwareize it, right? They wanted to run all the softwares, not in the proprietary hardware, but in the commercial off-the-shelf hardware, and take benefit of everything that cloud provides, right? Virtualization, multi-tenancy, elasticity, and so on. So that's the concept of NFV. NFV is nothing but you can think of a little bit differently, right? If you wanted to remember it in a different way. NFV is nothing but a name given for cloudification on the telecom service providers world, right? That's the easiest way to kind of understand. Now, when you talk about this, then it's basically the network functions, right? So mostly the wireless network functions. This is how it is kind of connected. So you have applications running in the cloud, the network functions running in the cloud / NFV, right? And the SDN controller running in the cloud / NFV. But now you can run everything in the cloud, everything in local cloud, NFV, or you can distribute it across multiple clouds. You can have a cloud in regional, edge, far edge, close edge. I mean, wherever you put data centers, everything becomes cloud, right? You can give different names to it, regional, national, and et cetera, right? But end of the day, in all these data centers, in all these cloud, nowadays it so happened. Initially, it was like this, right? For understanding, applications was running in the cloud, network functions was running in the NFV cloud, right? And then SDN was coming in mostly private clouds. But then now you can run anything and everything in every cloud, right? So there's no kind of really a thing. Wherever the data center is there, you can run. So the only difference now is in order for you to do that, you need to adopt microservice architecture. That's the only thing, right? Before when you're building a product, you can build a client application and server application. Now it's not like that because you can put your product software code in multiple places depending on multiple use cases and the requirement. You have to build your product from monolithic architecture, which is a client server based model, to a cloud native architecture, meaning microservice based model, right? So you got to build everything as a microservice, and all the microservices can connect and talk with each other through the RESTful API. So you can put some microservices in regional, some in national, some in far edge, some in close edge, some in device, so that all these different microservices come together and perform the function of the product that you're trying to build, or a solution that you're trying to build. That is how things has evolved. Guys, so far so good, right?
Yes, Parag.
Yeah. So now going to a little bit deeper. This is another hand diagram that I kind of drew for you guys, right? Just to kind of give you an understanding why nowadays everything can be run in everywhere, right? It's not like it's your own use case, money, and different things is allowing you to run everything in everywhere. So if you look at this diagram, so it's a legacy, right? Normally your VMs are there in the OpenStack or whatnot, right? And then you have your routers, different routers having a control plane and user plane, right? The BGF protocol and fastpath protocol and so on. This is how it used to be. Then SDN came into the picture where you basically put an SDN controller here, and that controlled the low-cost switches and tells, okay, if the packet comes here, send it here, send it here, send it here. All the control was here, right? SDN controller. And there is no NFV here, right? Right now, it's just the SDN, right? This is the legacy, and then this is the SDN that they introduced. Then, you can put the SDN controller anywhere, right? So you can put the SDN controller in a VM, or you can put it as a small add-on app within some network functions like MME or P gateway. You can have a MME P gateway, and then you can have a SDN function, and then you can use that SDN function to instruct the bare metal to pass the data, right? So you can put SDN anywhere. And now what happened is SDN controller became part of became one network function or part of some other network functions, right? And then you can also put here other network functions, right? Like MME, P gateway, and so on. Now, and you can also put here applications like database applications and so on, right? You can mix and match in any ways. That's the thought process. Now, when you think about SDN controller, you can put anywhere. Controller can be anywhere. It depends upon how you're designing, right? This is one of the diagram from the 3GPP spec that you can put SDN controller as a part of Vim. You can put SDN controller as a part of VNF, which is what I told you. P gateway can have an SDN controller. You can put SDN controller in the vSwitch. You can put SDN controller as a physical equipment, PNFs, or even you can put SDN controller in OSS and BSS. There's a number of options that you can put SDN controller. Likewise, you can put network functions anywhere, right? And things like that, right? It's kind of, you have to think like this. So most of the time we say this is the network function, right? VNFs. And then what about the VNF manager? What about the orchestrator? This is also software pieces, right? Even this sits in the VM or container, right? So that, or it can sit in the physical equipment, right? So it's depending upon how you wanted to develop and design, you can put all these, because end of the day, what you need to understand in the big picture is the concept. And then the second big picture of end of the day, it's all software, right? So you can put, depending upon what it makes sense for the use case that you're addressing, you can put VNFs, network functions, controllers, orchestrators, wherever you want, however you want to manage them, right? So that's the key thing that you need to understand. And different companies will have a different ways of doing things, right? So now let's get into a little bit more details. This is what I wanted to really achieve in the next 15 to 20 minutes. And then Yokesh will talk about the containers. So I'll take some time here because once you understand this, everything else is the same, right? What you need to understand here is the concept. So now if you look at this diagram, right, NFV diagram. So in the bottom, hardware resources, you need three things. We all are taught in our college times itself, right? We need compute resources, we need storage resources, and we need network resources. And when you have resources, right, you need a manager. That's the most important thing, right? So you have these three physical resources and you need a manager that manages these three physical resources and provides it to us as a virtual resource. Virtual computing, virtual storage, and virtual network. So Vim is Virtual Infrastructure Manager. So virtual, the name itself says that, right? So the Virtual Infrastructure Manager basically manages the hardware infrastructure to offer a virtual infrastructure to us. VMs, right? So virtual infrastructure is basically virtual machines, right? And now in this whole thing, right? What's more important is there is something called as a virtualization layer here. So you have a physical hardware here, then you have a virtualization layer here. And then on top of that, you are provided with the virtual computing, virtual storage, and virtual network allocated in your VM, right? That's how it actually happens. So now this virtualization layer, what does it do? It basically abstracts the hardware from the virtual resources. Hardware resources. It abstracts the hardware resources and provide it as a virtual resource. Normally, in the virtualization layer, what you will have is like virtual switches, right? And then you will also have a virtual managers like EVM and so on, right? That's what you normally have. Okay, so its job is to abstract the physical hardware and provide it as a virtual hardware. That's virtual resources, right? Physical resources to virtual resources. That's its job. So this virtualized, now what you need to understand is the physical compute, storage, and network hardware. Virtualization converts that into virtual compute, storage, and network. And this whole functions is called as network function virtualization infrastructure. Okay, this is the name given to this whole block. And this whole block is managed by Virtual Infrastructure Manager. And to give a practical example, an OpenStack is the Virtual Infrastructure Manager, which can manage different hardwares with the virtualization switch and the EVMs and things like that and provide the virtual resources. So this is the first step. Now, here you can also provide containers, right? This diagram is more from the virtual machines, but you can also provide containers. So it's the same thing. In case of containers, you will have your container manager here, which provides the containers and abstracts the hardware resources and provides the containerized virtual resources. Right? So the concept is the same, right? But of course, there's a difference between a VM and container. As you know, the VM, every VM has its own operating system. Container shares the operating system. That's the difference, right? Both has its positives and negatives, right? Depending upon your use case, you will choose what is good for you, what is not good for you, right? But from the NFVI and VIM point of view, it's nothing but there is some manager which manages. Right hand side is a manager which manages this block. So virtualized infrastructure manager manages network function virtualization infrastructure block, which has the hardware and some software that provides you the virtual resources. That's the first step you need to understand. Now, when the virtual compute, storage, and networks are available, when you are providing the virtual resources, what does it mean? You're actually providing a VM or a multiple VM. So you can install your MME in one VM, or if MME is designed as a multi-VM architecture, you can put 5 or 6 VMs and you can build an MME, right? So that becomes your virtual network functions, right? The MME example is a virtual network function. So now this virtual network function has to be managed. Like how this hardware has to be managed by the virtualization layer, like that this virtualized network function has to be managed. That is managed by the element system. So you can think of, if you take from Magma, you can think Magma is a virtual, just as a a converged virtual network function, and your NMS and orchestrator, NMS and EMS, that whatever that you have, right? You can consider that as something that manages that Magma core. So that is an EMS. Okay, so every network function will have some manager. You have to have that manager, or you can have one manager that manages multiple network function. But nevertheless, you need to have some local manager that manages this virtual network function. And now this whole block, virtual network function and EMS, this is virtual network function block, requires a super manager. Like how you need a virtualized infrastructure manager, you need a super manager to manage all the VNFs. That's called as a VNF manager. You can have one VNF manager managing all the VNFs. You can have multiple VNF manager managing different VNFs. It depends how you want it to architect. But what's important is the second next layer is the actual network function layer, where your MMEs, P gateways, everything sit together. That is locally managed by EMS, together managed by the VNF manager. That's the most important thing, right? Now once you understand that layer, then comes your next layer. In every telecom architecture, right? You have something called as a OSS and BSS. It's very important, right? So you have so many hardwares and so many network functions and so on, right? So how do you operate all of them? How do you make sure it is running 24/7? How do you run the network operating center, right? So all those, you have to run them and make sure everything is running properly, right? So that's normally called as an OSS, operating support system, right? Ensuring that you are able to run this whole thing, right? NFVI, virtual infrastructure manager, VNF manager, and the VNF layer, and the virtual, both the layers, we want to make sure everything is working fine, right? From hardware to the software to the virtual functions to its manager to everything, right? So that's done by OSS. And then the other key component is the BSS, billing support system. Now you're deploying this whole network for what? For providing services to your subscribers. So you need to have some connection to your subscribers. Well, how much he is paid, depending upon his payment, what function to enable, what function to disable, and how much billing that we have to do. And all those kind of things is done by the BSS. Right? So there are architectures where OSS feeds to the BSS. There are architecture that OSS just manages the network and BSS has some mediation layer that collects all the different counters from all these different devices and gives it to the BSS system, and then BSS system does everything that has to be done towards the customer. Okay, so that is the next most important layer. Okay, then now this layer and everything has to be managed, automated, orchestrated. So that is nothing but the top orchestrator. Sometimes it's called as a resource orchestrator. Sometimes it's called as a service orchestrator, or sometimes it's called as resource and service orchestrator, right? So this is the master orchestrator that manages all the resources, manages all the services, because all these network function, what does it do? If you connect all these network function, you are able to offer services. What services? As an example, voice over LTE. As an example, broadband, right? So you can manage the network resources using resource orchestrator. You can manage the services using service orchestrator. And this is the most important thing that you need to understand. If you understand this, everything is pretty easy, right? So I'll just do a recap. The bottom layer is all about hardware. How do you change the hardware to provide it as a virtualized layer? And how do you manage them? That's the first layer. And the second layer is the actual your network functions, the wireless network functions, right? Like MMEs, P gateways, eNode Bs, whatnot, right? ORAN, eNode Bs, whatnot. And its manager and the global manager that manages this whole thing, right? As an example here, this EMS manager can manage P gateway. Now this VNF manager can manage MME, P gateway, and S gateway and connects all of this together. And also eNode B connects to the eNode B and then make sure that the whole service is built, right? So those kind of instructions is provided by orchestrator to the VNF manager to do that. Then the next third layer is managing this whole network and ensuring the customers is built right and operating this whole network and automating this whole network. That's your next layer. So it goes layer by layer, right? The automation goes layer by layer up and abstraction as well goes layer by layer up, right? So this is the most important concept that you need to understand. Once you understand this, it becomes easy, right? So whatever I told you is what is mentioned in this. So if you actually look at it, the next key concept is the interfaces, right? It's very difficult for you to remember these interfaces, but what I told you is what will be defined in interface. Like for example, if you look at this interface between virtualization layer and the hardware layer, what does it do? It creates execution environment for VNF, collects hardware state information, and manages VNF without being hardware dependent. So this basically abstracts the hardware layer. That's what it does. Now, if you go to the next layer here, it provides the execution environment for VNF for NFVI, right? So it basically provides. In this case, it's only VM, right? And then VM is given, one or multiple VM is given, so VNF can be formed. And that abstraction is provided by this layer. And this layer, what does it do? It basically ensures it gets policies, it gets accounting data, whatever is required, so it can do the OSS and BSS functionality, right? And this layer, what does it do? This layer instructs this layer instructs this layer further does this, right? And different levels of abstraction. So this layer basically provides, resource related request. This layer, at the service level and the VNF level, and then this VNF manager translates that into the VM level and provides that. So it's like this. Okay, orchestrator will say I need to build an end-to-end 4G service. VNF will connect all the different VNFs that are required to build the 4G service. Now, in order for us to do it, requires a VM. So it goes and tells the virtualized infrastructure manager to give the VM. So once the virtualized infrastructure gives the VM, it puts all the P gateway, S gateway, and everything, builds the network, and then it tells to the orchestrator it's all good, and then we are good to go live, right? So that's how it happens. So if you could understand the basic thing that I explained in the previous slide, this slide basically explains that. And normally when you explain, you basically explain it, what this box does, and what kind of a data it communicates between two different boxes. And that is called as an interface or reference point. Okay. And there are multiple interfaces and reference points are defined. So when you are building this OSS BSS, when you are building this EMS, when you are communicating with the VNF manager, you have to follow that protocol. It's nothing but HTTP, right? Most of the time, right? You got to follow that protocol and ensure that you are able to kind of implement that IO, what is required, so the communication can happen. Use the compute resources to compute, storage resources to store, and IO resources to communicate, which is a protocol that goes back and forth. Okay, and this is something that I already told you guys earlier. Why Nfv architecture? Because it provides a lot of advantages, same as cloud, from elasticity to portability. I can move MME from India to Canada, Canada to India. Ensure no point of time, nothing is down because you can bring it up quickly and do stuff. Security, service continuity, assurance, which is collecting the data. OSS is part of assurance, is a part of OSS. Operations and management is part of OSS. It's energy efficient. You're not running a dedicated high-end hardware, right? And you can even do it in a way that it runs with the existing network, that is hardware network. So all these are the advantages of NFV architecture. Okay, I'll pause here, guys. So far, so good.
Yes, Khaled.
Yes, Khaled.
Nice. Now, what I explained, I drew this diagram for you guys to give little clarity to what I explained, right? So if you look at this, what happens at the lower layer, like I told you, it provides the VM, right? Then one level up, it's a VNF. So you can use I have used 3 VMs to make one VNF. So that means let's assume that one MME requires 3 VMs and each VMs is VNFC. Right, so you can build your architecture of MME into multiple microservices, and you can even instantiate, deinstantiate individual microservices within the VNF for the scalability of the VNF. So you can either design one VM as one VNF, or you can define multiple VM combined performs the function of one VNF. In case example MME, example AMF, right? That's the clarity that I wanted to give you. Drew this diagram, right? So you have multiple VMs provided by the virtual infrastructure manager, and you can pick the VMs, how many ever you need to build your VNF, and then you build your VNFs. And then on next level in the service and resource orchestration, you connect all those VNFs and you make a network service, meaning a complete end-to-end network. If you take from the core P gateway, S gateway, and MME, you connect these and you say this is the core network service. And if you put it in the cloud, it becomes core network as a service and offered to others, right? So the concept is pretty straightforward, right? How it's all gets connected. So here you have VM, then you build VNFs and you connect the VNFs and you form the network service. And that's the clarity that I wanted to give. And each of these places, you have respective functions that has to be implemented to make this. In this level, you need to manage the resource management, VM management, right? In this level, you have to do a VNF management, lifecycle management. VNF is instantiated, brought it live, terminated, configuring the VNF through the EMS. And likewise, network service, the same thing, right? Lifecycle management of the network service. If the whole network service goes down, what should I do? If some VNF goes down within the network service, what should I do? Like that, there is a number of functions that are defined by the standards for you guys to kind of understand that. Okay, so far so good. Let me check. I may not be able to complete. Okay, so what will I do is I will kind of pause here. See, so far what I covered, just to give you guys, right? We talked about the bottom layer, VNF layer, and the master orchestrator layer, right? There's one thing that I did not talk to you guys about is there is something called as a descriptors, right? That SCMA. So I wanted to kind of explain that SCMA as this. In a very simplest way, what I wanted to say here is that if you have worked in OpenStack, you have this heap template, right? If you have worked in container, you have some templates. And if you work in anything, it's a template. So what is a template? Template is, it's like this, right? When you write a program, you first provide some input, and then you write a business logic, and then you have an output. So if you wanted to make this whole thing work, right, it's the input for all these things are the templates that you provide, whether it is a container-based system, network VM-based system, or the combination of the systems. What you do is you basically provide some kind of input files, and those input files basically allows the system to get itself boot up and be ready, right, based on the instructions that you are providing in that input file. Right, so that is called theoretically, right, a descriptor. So if you are actually building a physical network function, there is some template that tells you this is the capabilities of this physical network function, and get this physical network configured. You have to configure this physical network function based on that template. And if you're doing the same thing for VM, you do heat, right? Heat template. So in the VNF, they call it as theoretically VNFD, VNF descriptor. Then the network function, you have NSD, network service descriptor, VNF forwarding graph descriptor, and virtual link descriptor. What does it mean? So the virtual link descriptor that connects the two VMs or VNFs. And then one next level is, sorry, the virtual link VLD connects two VMs within the VNF, like the previous one that I showed, right? Two VNFC within the VNF, it connects, right? And then if you wanted to connect all the VNFs together, right, like this, then that is instructed by this, right? So first you say connect this port to this port of two VMs and then build MME, then connect MME to P gateway, that is done by VNF FGD. Then the whole service, right? Not only the core RAN and everything, right? Network service that's done by NSD. So it's kind of different template for you to build low level, next level, and next level, right? So that is how it is actually done. It's called as a network service catalog. Okay. And what you need to really understand is these files are very, very important to onboard and make the network live. It's very, very important. So even when you are building your Magma distro or anything, you have to have a template file that people can just do it. And with your package, automatically it installs and gets it up and running, whether it is a container or VM. And I believe we already have that, right, in the open source, Yokesh, if I'm not wrong.
Yes,
Right, Yokesh?
correct. Yes,
Yeah.
correct.
It may be called as a different names, right? But what's important for you to understand the concept? It's called as descriptor. Without descriptor and the actual executables, the binaries, you cannot get it up and running in OpenStack environment or in a container environment, right? Nowadays, every products are provided with descriptors and the executables. Now, once it is up and running, right? After that, what happens is all these files keep changing. Why? Because some new traffic comes, you need to instantiate another MME. If less traffic, you need to deinstantiate another MME. So the network service templates will change. And you might have to add new VMs. So your VNFD template changes, VNF template changes. You need to add new PNF, PNF template changes. Configuration, you might increase the resources, decrease the resources. You might restrict some subscribers, not restrict some subscribers. You might stop someone because of the security reason. So dynamically, the different things changes, right? So when it becomes online, the initial templates that you have may not be applicable, right? So it keeps changing. So in order to keep on updating that running instance of that template, it's called as this, right? This change that happens, right? This change is also kept tracked. So this one, you can understand that this one gives at any point of time the current state of the network, and the left hand side gives at any point of time how the network was first onboarded and brought it up. And you need these two things, understanding, very, very important, right? So this is called as a descriptor. This is called as a resource, network service resource, virtual link resource. So these are the dynamically updated files. So when you look at in your Magma, also you will have the onboarded file, and you can, at a given point of time, how it is changed and things like that. In the cloud, you can actually see another file that has the latest update on that, right? This is the current structure of the NS files and so on. But this is the concept that you need to really, really remember. There is a descriptor files, allows you to onboard and get the system up and running. And there is a resource file. Name could be different in different places, but there is a resource file that keeps the current state of the system, how it looks, how the network looks. Okay, so now this is the last slide. I will stop here, right? So this is how it is. It's pretty straightforward, right? You have a physical switch, virtual switch, physical switch, virtual switch, and you have multiple VNFs, and you have a physical network function, then you have your endpoint A, endpoint B. So kind of explains what it is, right? So you can have multiple network infrastructures, you can have multiple orchestrators, you can have different types, right? And different POPs. But what's more important is you need to understand if you connect all the network function, it's called as a network function forwarding graph. That's what is this VNFFGD, right? Network function forwarding graph. Then when phone to phone, the whole thing is called as a end-to-end service, right? That's your NSD, right? So this is the whole thing is called as a network service. This is called as a network functions forwarding graph. And between VNF and VNF is called as a VNF forwarding graph, right? Just to kind of help you understand what does it actually mean. I kind of put this diagram in. So I'll pause here and we will look through, what I wanted to really do is I wanted to achieve, what is edge computing, and then get into all these projects and understand what these different projects based on the understanding of these different components that we learned. That will give you a complete big picture. And that's what I wanted to achieve. But, we're running out of time. So we will do this 2 slides and a few other additional slides in our next session. But hopefully, it was clear. What I wanted to achieve is give you a big picture of how this whole network function, the latest network function, and the concepts around that, So you kind of able to map to the actual things that you do on grounds, how you build your products, how do you build Magma products, how you build non-Magma products, how you deploy, how do you run it, right? So that's the biggest thing that I wanted to achieve from the concept level, and I believe I have achieved. So with that, I will hand over the session to Yokesh. Yokesh, you mentioned you need 20 to 25 minutes. The floor is all yours.
Sure. Thanks, Karan. Yeah, I think people just start doing hands-on, but getting the big picture is the main thing. I think all your sessions are covering the big picture, and what we are trying from our side is we can map it to the real world and see the theory and practical practice goes in hand in hand. So with that, I would just summarize what we have covered till now, and then I will open the floor I'll hand it over to Shivesh and Sridhar. So what we have covered in our previous sessions was the basic registration, like how UE GLB gets registers with AGW, how UE is authenticated, registered. So that means all the security checks are cleared and it's an authentic user. And with that, we know what are the kind of services that has to be provided. And then when the UE actually wants to touch the internet, what kind of policies, rules is that they are going to be deployed. We have been uh, showing a couple of flavors. One flavor was with orchestration. One flavor is without orchestration. So orchestration in the sense you will have all GUI dashboards, and then you can configure the things. Then you have a CLI flavor where you can actually put in the CLI and do the stuff. So we have seen those two flavors. We've seen the orchestration architecture, and we have seen the SUSI encryption. Now, what we are going to cover in this session is how these things are coming together from the containerized point of view, how it happens, how the Docker goes with the orchestrator, how it is in headless mode, and then the power of the Dockers when you restart your services and everything is as is, and that makes it cloud ready. So it just the demo tries to show how we can be cloud ready with this Docker infrastructure. So with that, Shivesh, I'll share my screen, and I think you can go through it. Okay.
Yeah.
And I'll do the demo. Okay.
Yeah.
So just give me a second. I'll share my screen. Shivesh, I think my screen is visible, right?
Yeah, it's visible. So, shall I start? Yeah. So, as we all know that Access Gateway up till now is deployed as a standalone module, which obviously had some limitations like we can't restart individual services, and also the main thing is that there is a duplicating. If we want to duplicate the deployment on other systems, like on machine one and machine two, we we want to have a same kind of deployment, and it becomes a tedious task, right? Because we have to copy the code from here and there, the binary, and then rebuild the binary and install it. So it's a tedious process too. So to improve upon all these things, we needed to containerize the access gateway like other modules like orchestrator and feg are already containerized, right? So here we'll have a look how we can mm, dockerize the access gateway and then connect it to the orchestrator and NMS. And we'll also have a basic end-to-end 5G call flow, and then Sridhar will also test some stateless features also with it in the headless mode.
Shreyas, one quick question. So you put the whole A gateway in container, or do you split
No,
functions of A gateway and put it
yeah,
in multiple containers?
yeah. We split it into multiple containers based on the services. Like here in the architecture diagram, the control proxy would be a separate container, MME, SMDB, all these services will be of a separate container. So we can have a more control over all the services, and we can automate the processes as well easily. But the one thing is that the OVS part is still not containerized because it's very tightly coupled to the Linux kernel. So as we move forward, we'll have to containerize this OVS thing as well. Then we're also able to take the benefit of scaling up and scaling down the access gateway services. Yeah, next slide. So this is the screenshot of the Docker containers that will come up for access gateway. Like you can see, the Docker containers are separate for separate services like session-D, state, directory-D, policy-DB, and all. So what are the benefits of this? The benefit is that the services can be decoupled and managed independently. For example, we have multiple configuration YAML files. So for a particular service. So if we want to change the configuration of a particular service, say pipeline YAML. So in the standalone access gateway, if we change any one of the configuration file, we had to restart the whole Magma services, but of access gateway. But here we can easily go by just restarting the pipeline D container, and rest will keep on working. And we can go for smoother software updates and based on the configuration, and then obviously we can deploy it easily on other systems using pre-built Docker images. We can operate and automate it using various scripts like using Ansible, YAML scripts and all. And the prospects, like I said, that we can bring the fast path OVS component in the containerized periphery, which is tightly coupled with Linux kernel right now. Then we can have the full benefit of scaling services. So here, this slide, these screenshots depict the enablement of the 5G features on the access gateway using orchestrator. So this is the Swagger API part through which we can just update the flag and then enable the 5G features. You can see these two on the next slide. You can see the two ports are enabled. One is for LTE traffic and another one is for 5G traffic.
Yes, thank you, Shivesh. That is the how we can brought up the Dockerized HW. So we will test stateless future also on the Dockerized HW. But before going to testings, let us see basic about what is stateless future. Stateless future enables the decoupling of the state data and the state functions. This is achieved by storing the state data in a persistent storage. Why is stateless future needed is it provides failure recovery and also it enables auto scaling and high availability. So next slide. So in this slide we will see what is comparison between the stateful and stateless. Normally HW will be done as stateful mode where UE is register connected to the access gateway. So if in the middle, if access gateway got crashed, then all the UE related data will be lost, state data will be lost. So UE want to re-register again in the newly spanned HW. So it will lost its ongoing services also. So to overcome this problem, we will implement the stateless. So where UE will connected to the access gateway and all the state data will be synced into the Redis DB. So if UE access gateway one got crashed, so on the access gateway two will get up and it will retrieve the data from the Redis DB, and UE will continue its services with short delay. So this is how stateless is useful, and we will check one. We will test the status switcher using the Dockerized HW. So and the demo how this is connected. So simulator is connected to a HW, and it is connected to the HW is connected to orchestrator. Using this demo, using this thing, Shivesh will show the demo. And in the next slide, so we will see stateless future testing in headless mode. So where we will concentrate mainly on the MMA, that is, so we will try to delete this container and bring up the MMA container again, but there won't be any delay or any re-register of the UE, any delay in the process. So how to delete a container? So next slide. So how to delete a specific container is, so we should use sudo docker compose rm minus s minus v container name. This will delete a specific container, and we can respam the specific container using the up command. So
I think we'll just hold on. So I think what Shivesh and Sridhar are going to demo is how the complete 5G feature works in Dockerized, and how in event of any restarts or failures, things will be booted up without any disruption of the existing services. So yeah. So Shivesh, I'll start with the Dockerized AGW with orchestrator.
Yeah. So first we'll create a simple Vagrant file and bring it up. Once it's up, we can download the access gateway install Docker script from master Magma GitHub page. And once it's done, we have to match the interface names as given in the script, which we'll do. After doing this, we will reload the Vagrant VM.
What we're basically doing is we are kind of renaming the interface names as ETH1, ETH2 because a lot of the YAML files use the same. So the default Ubuntu names it differently. So we bring it with the same name. So a lot of the configurations can be used as is.
Now we'll relog in into the Vagrant VM, and then you can skip for a minute.
Sure.
Yeah. Now we'll give the orchestrator certificate with which we want to register our access gateway with. So we'll copy the contents of the root.c file of orchestrator into the access gateway so that they can connect later. Now we will execute that script. This is basically an Ansible kind of script which installs the basic packages that are required for the building up of Dockers. Once it's done, we'll again reload the VM. Now we'll clone the Magma repo. You can skip a minute. This patch thing we can ignore because it will be modified in the newer code. So now here we are adding a additional repo link through which the Docker files can get the packages from. Now we'll go to the Docker location and build the Docker images. We can check there no images are made. Now we start the building of the image. You can skip 4 or 5 minutes. All this process of image building. Yeah. So once the images are made, we can see these access gateway Python and access gateway C images basically are used, and then we can execute either this script or we can simply do sudo docker compose upd to bring all the containers up. Now you can see all the containers are starting. They generally start within a minute or two. Like you can see all the containers are up here. Now we'll connect it to the orchestrator using NMS. Basically what we have to do is click on add gateway on NMS and then place the hardware ID and challenge key into the pop-up form, gateway form. And then it will add the gateway, register it with the orchestrator and NMS. So you can see the gateway on NMS, and now we'll check the same thing in the access gateway as well, this second CLI script. So all the things are successful. That means it's connected. Now we'll check the subscriber list. You can go 1 minute forward. Yeah. So it's also syncing the subscribers. Now we'll check if the 5G features are enabled or not using get request. If it's not enabled, then using put we will enable 5G features flag here. So here the value is false. We have to make it true. We'll do it using put request. So We'll check again. The flag has changed. Yes, it became true now. Now we'll check on access gateway as well. So all the flags are true. So now we'll add a new subscriber here through NMS and use it for our to make our end-to-end 5G call flow. So we have added this subscriber through NMS. Now we'll check if it is synced in the access gateway. It usually takes 4 to 5 minutes, but here we have fastened the speed. Now we'll configure the access gateway values in our simulator, our GNB and UE simulator. So we'll have to configure the MC value, MCC, MNC value, which we have in the access gateway into our simulator and provide the IP address of the access gateway as well. Once the configuration is done, we'll run the GNB and UE. Here we have to also provide the simulator IP address. Now we'll start the TCP dump for capturing data and the access gateway, and we'll start the GNB and UE on our simulator. You can see as per the associations, both are sending and receiving data. The access gateway as from the simulator. Now we can also check the PCAP file that is captured in the access gateway. For that, we need to download the PCAP file and open it through Wireshark. This 5G call flow PCAP file is generated. Now we'll download it and analyze it in the Wireshark. So as you can see, all the EDU session resource response, all the things are coming up. So that's it. Now from here, Sridhar will show his demo to test out the stateless feature.
Okay, thanks, Shivesh. So I think what we've seen is one flavor of the configuration using Dockers. What we are going to show is a headless node. I don't know if the time is okay or.
Okay.
Maybe
We can continue. Yeah, that should be okay. So the headless mode we can show in our next session and followed by Parthiban, maybe 4G call flow, end-to-end system, right? And then in the last session, 5G call flow end-to-end session. That would be a good closure with real equipment. Does that sound okay?
Sure, Kader. Yeah, I was also thinking on the same.
Yeah, perfect. That will allow me also on the theoretical side to cover a little bit more technologies and spectrum point of view, right? So that will be good. All right, so we can continue in our next session, Suresh. How long, how much more time for that demo, if you don't mind?
Yeah, so give me a second.
It's 5 minutes.
Just 5 minutes. So
yeah, if you want to cover it, go ahead. Let's close on that. Yeah, please.
So Sridhar.
Yes. Yes, Yogesh, yes. We will see it fast because Shivesh already showed how to make the Docker, how to connect the MC, etc. We will just see how the traffic flow and the stateless future.
So just to give an overview, I think.
So please share your screen, Yogesh.
Sure. I missed it. So here, what Sridhar is showing is the another flavor of configuration, where the headless mode is there, like means there is no orchestration, and via CLI is configure everything. Parameters are all same, but it is explicitly spelled in the CLI. So yeah.
Yes, so we have configured so Docker's HW in headless mode. So we have configured in headless mode. So we want to add subscribers using CLI command. First, we want to add auth key, OPC, and MC. So and then we will check is the MC got or not. So you can move forward. So you can move forward. Yes, auth key. Yes, now using this command, we will add the APN and Amber key values into the MC. So you can move forward. So yes, we have run this command, and if we get the MC again, so we can see APN and Amber values got added. So yes, now all the setup is okay. So let's check the HTTP ports are up and running. So yes. HTTP ports, both ports are up and running. So in the one terminal, we will capture the packet pickup using TCP dump, and in one terminal, we will run the GNB. In one terminal of UE ransom, we will run the UE. Yes, we got PD session. So we are testing the pinging using the terminal. So ping is working, traffic is flowing. So now we will try to test the stateless future. So firstly we will grab the OAI MME Docker to get the Docker number, just to check that we are deleting the Docker number and we will respawn new one. So yes, using that grep command. It is the Docker number. So for the OAI MME, so now we want to go to Docker Compose to folder where Docker Compose file is there, and we want to remove it. Yes, you can run. So using the below command, as I told in the PPT, we can remove the Docker. Here we are removing the OAI MME. So now, yes, you can move forward. Yes, if we grab again, yes, now there is no Docker container. So we will respawn the new one by using the up command. Yes, you can move forward. So yes, we can see clearly that new Docker MME has been spanned. So now our target, so now the target is there should be no disturb in the call flow. So to check that one, we will release the PDU and get the PDU again by using the CLI command. So first we will release the PDU. The CLI command will release the PDU and also get the new PDU session. So the PD session is released. Yes, you can move forward little bit. So yes, PDO session again got set up. So to check the continuity, we will check the traffic once again. Yes, traffic is also flowing without any disruption. So let's now stop the so let's see the OVS table once. So OVS table 13 to check how. So once we get the PDO on page, we will check the traffic. So the basic OVS table will come up, will come one for up and one for down. Both came up. So now we will stop everything and we will download the pick app. Yes, you can move forward. So if we open the pick app, so everything registration, authentication, security command, everything we got PDO session and traffic is flowing. And after some time we have released and we got new PD session, and after again traffic is flowing. Using this one we are showing that we can test stateless future using Dockerized HW.
I think what Sridhar wanted to cover was even though we killed and restarted the MME, we don't have to re-register, and PDU got released properly. If it would have been in local memory, we could not release the PDU, and the PDU got re-established, and that traffic was all going through. Yeah, so I think that's all from our side, Kader. Back to you.
Thank you so much, Yokesh and team. Shivesh, Sridhar, as usual, right? Good job. No, I'm proud of you guys. Thanks for supporting this initiative. You all have a wonderful evening.
Thank you, Kader.
Morning, wherever you guys are attending from. Take care and talk to you all soon. Bye-bye.
Bye. Bye. Thank you.
Thank you, sir. Bye.
Thanks, everyone.
Thank you, everyone. Thank you.